So picture this, right? We've got a kangaroo and he's just gone to the gym and he's just hit legs, right? And then he's trying to jump to his car. However, every time he jumps out of the door from the gym to his car, he's only able to jump half the distance that he just jumped. Okay, and so his car is 20 meters away, right? And so his first jump, he's able to do a big leap, a 10-meter jump. Okay, but then the second jump is 5 meters. Okay, and then the third jump is 2.5 meters. And the fourth jump is a 1.25 meters, and so on. And so we ask the question, well, is Skippy ever going to get to his car? All right, now we can whiteboard this out. Okay, where we can actually see the common ratios are half. Okay, because we're just multiplying each term by half. And so that means, well, we can find the general term. We've seen this before. It's t of 1 times by r to the power of n minus 1. And so I just want to know, right, okay, if he's still jumping to his car, right, what about the 20th jump? Okay, how far has he jumped on his 20th jump? All right, so we get to this point here, and I just want to highlight something important, okay, is when we've got a half here, this 10, okay, 10 multiplied by the ratio, that's 1 to the power of 19 over 2 to the power of 19. Now 1 to the power of 19 is just 1, right? So it's 1 divided by 2 to the power of 19, and 2 to the power of 19 is a really, really large number. Right, so you throw that in your calculator, okay, and so you get something really, really small. So on this kangaroo's 20th jump to his car, millimeters, right? It's a really small jump, okay? And so the question is he ever gonna make it to his car so he can get home and have some post-workout and stay anabolic? And so the way that we'd answer this question is, well, we'd say, okay, let's consider the sum of his jumps, because 10 meters plus 5 meters, well, that gets him 15 meters of the way through to his car. What about 20 jumps? How far has he traveled in 20 jumps? So we consider the sum. To recall the sum formula, okay, we can plug it in, use a graphics calculator. Okay, one thing I do want to point out though is that this is a very, very small number. Okay, just like it was down here, just to point out. So that's going to be a really, really small number. Okay, so you put it in your calculator, and the sum of his jumps after 20 jumps is 19.999, I think there's another 9 in there, 8 meters, right? It's really, really close to the car. But he's not at the car, he's still like small bits off. And so my question is, if the kangaroo keeps jumping forever, like forever, will he ever get to the car when he's only got this tiny amount to go, right? He's just got to get that small amount right up to 20. And so when we are talking about the jumping forever, we're talking about this concept of infinity. Okay, so where I don't want to know the sum of 20 jumps, I want to know the sum, and I'll give this a little title here, we're introducing infinity here. I want to know the sum of infinity jumps. All right, and so that would just be using the same formula as above here, just using this one. Okay, and so we're encountered with something like this, right? It says t of 1, 1 minus r to the power of infinity instead. Okay, this is the perfect point to highlight, is that this r to the power of infinity is going to eventually equal 0. Like it's going to limit off to 0 as the power goes that high, when r is a fraction. Okay, so you kind of end up with something like this. It pans off towards 0 when you raise the power to infinity, so you eventually get this formula here, which is just so nice and sleek. It's like this, it's just so compact, and it's like to infinity, right? But we want to see, does the kangaroo ever make it to his car? And so we can go, well, the first term was 10 over 1 minus a half. We simplified out 10 over a half, that's equal to 20. Okay, so if the kangaroo jumped infinitely many times, he'd eventually make it to his car. Okay, so I'm gonna propose another question here, right? And that is, does 0.999999999 equal 1? Short answer, yes, okay. But how? Okay, and I just want you to consider this for a moment. Okay, 0.9 is equal to 9/10, and 0.09 is equal to 9/100. So you can make a bit of a deduction and say, therefore, 0.99 is equal to 9/10 plus 9/100. And this pattern can continue, right? So if you kind of did this for 0.009 and then you added 9/1000ths, what you would get, 0.99999 recurring, would be equal to 9/10 plus 9/100 plus 9/1000 plus yada yada yada. And what actually forms from that is a geometric sequence, because if you just considered this list of numbers right here, T of 1 is equal to 9/10, T of 2 is equal to 9/100, T of 3 is equal to 9/1000, and so on. And what we're really saying here is, well, we can spot a common ratio. It's a 10th. We're just multiplying through by a 10th. So we've got R is equal to a 10th. And so what I'm saying is, if we had 0.99999 recurring infinitely long, right, then what we have is we have got a geometric sequence here that goes infinitely long, and well, that means we can use our nice formula, which is the sum to infinity is equal to the first term over 1 minus r, and this only works when r is fractional between -1 and a +1, and that is the case here. R is 1/10. So we can plug it in. All right, the sum to infinity for this geometric sequence, the first term was 9/10 divided by 1 minus the ratio, which was 1/10. So you get 9/10 divided by 9/10, and something divided by itself is equal to 1. So then you make the deduction, therefore 0.9999 recurring infinitely is equal to 1. Kind of nice.